The bandwidth revolution. In 1969, the world watched the moon landing through a literal fog of technology, because Apollo 11 relied on analog radio waves with extremely low bandwidth, essentially a very narrow pipe for data. They could only transmit a tiny amount of information at a time. To get a moving image back to Earth, the signal had to be stripped down to a low-resolution, slow-scan format, resulting in the famous grainy, ghostly black and white footage. It was a miracle we saw anything at all, but the quality was so poor that it was often difficult to distinguish the astronauts from the lunar shadows. Artemis II, however, represents a system much closer to modern digital broadcasting than the Apollo-era approach. This mission utilized optical communications, a revolutionary system that uses infrared lasers rather than traditional radio waves to send data. Think of it as the difference between a dial-up modem and a modern fiber optic connection. Because laser light has a much higher frequency than radio, it can carry 10 to 100 times more data per second. This allowed the Artemis II crew to beam back ultra-high-definition, high-resolution video and crisp, full-color imagery in near real time. The shift represented the move from symbolic glimpses to total immersion. In 1969, the grainy footage was a byproduct of a system struggling just to maintain a basic connection across the void. For Artemis II, the laser-based system meant that every crater and mountain on the lunar far side was captured with unprecedented clarity. By replacing invisible radio waves with focused beams of light, NASA didn't just talk to the crew. They allowed the entire world to ride along in the cockpit, transforming the moon from a blurry, distant object into a vivid, high-definition reality. Deep space radiation protection. The Apollo 11 strategy for radiation protection was essentially a high-speed hit-and-run. The command module was a hollow aluminum cone, and NASA's primary defense was simply moving through the radioactive Van Allen belts as fast as possible. Van Allen belts are two massive donuts of radiation trapped by Earth's magnetic field. While the aluminum hull blocked some minor particles, it offered almost zero protection against a major solar event. The astronauts were effectively gambling on a clear space weather forecast, hoping the sun wouldn't have a massive eruption during their 8-day trip. Artemis II, however, transformed the spacecraft itself into a multi-layered fortress. While it used a high-strength aluminum-lithium hull, the internal engineering was the real game-changer. Unlike the hollow interior of Apollo, Orion was packed with hydrogen-rich materials, like water tanks, food storage, and plastic-lined equipment, placed directly against the walls of the capsule. Because hydrogen atoms are the most effective elements at absorbing and slowing down high-energy radiation, the ship's own pantry and plumbing acted as a permanent, passive biological shield. The shift represented the move from statistical luck to redundant defense. While Apollo relied on a quiet sun, Artemis II utilized a storm cellar philosophy. In the event of a sudden solar flare, the crew moved to the center of the ship and reconfigured the cabin by stacking heavy stowage bags into hot spots, where radiation was highest. This was supported by the hybrid sensor architecture, a network of active sensors that provided a real-time space weather report. This allowed the computer to warn the crew of incoming particles before they arrived, giving them time to hunker down. In 1969, the astronauts were passengers in a thin metal shell. For Artemis II, the ship was an intelligent machine designed to actively swallow the dangers of the void. A trophy versus common ground. In 1969, the Apollo program was a closed, nationalist project. It was born from the space race, a period of intense geopolitical rivalry, where space was the ultimate battlefield for ideological supremacy. To NASA, cooperation meant hiring private American contractors to build a purely American machine. The goal was to plant one specific flag on the moon, to prove that one specific government had the superior technology. It was a winner-take-all sprint, where the Soviet Union was the enemy and the rest of the world were simply spectators. Artemis II, however, was built on the foundation of the Artemis Accords, a massive international treaty that turned the moon from a battlefield into a global laboratory. This mission wasn't just a NASA project. It was a collaborative effort that integrated hardware and brainpower from across the planet. The most critical component of the ship, the European Service Module, was provided by the European Space Agency. This module provided the power, water, and air for the crew, meaning that the American Orion capsule literally could not breathe without its European counterpart. The shift represented the move from isolation to interdependence. While Apollo was a solo mission, the Artemis II crew reflected a global alliance, featuring the first Canadian astronaut to leave Earth's orbit as part of a partnership with the Canadian Space Agency. Instead of competing to see who could reach the finish line first, These nations pooled their resources to build sustainable infrastructure that no single country could afford or maintain alone. In 1969, the moon was a trophy to be claimed. For Artemis II, it was a common ground where international partners worked together to ensure that when humanity returns to the stars, we go as a united species, targeting miles to meters. In 1969, landing on the moon was a manual, high-stakes game of visual navigation. Apollo 11 relied on dead reckoning, a method of calculating position based on a previously determined point, combined with the astronauts looking out the window to find a safe spot. Because the onboard computers were limited, the landing footprint, or target zone, was an enormous oval stretching miles across the lunar surface. Neil Armstrong famously had to take manual control of the lunar module to steer it away from a boulder-strewn crater at the last second. It was a successful landing, but it was imprecise. They landed miles away from their original target point because the technology simply couldn't account for every orbital variable. Artemis II, while a flyby mission, was the ultimate test for a technology called terrain relative navigation. Unlike Apollo, which used basic radar and human eyes, the Artemis system used high-speed cameras and sensors to see the lunar surface in real time. As the spacecraft soared past the moon, the TRN system took rapid-fire photos of the craters and ridges below, comparing them instantly to a preloaded digital map. This allowed the onboard computer to calculate the ship's position within just a few meters, a level of accuracy that was physically impossible in the 1960s. The shift represented the move from approximate zones to pinpoint accuracy. In the Apollo era, as long as you hit the general Sea of Tranquility, the mission was a success. For the Artemis program, precision is a requirement for survival. Because future missions aim to land at the lunar South Pole, a treacherous landscape of deep shadows and jagged peaks, NASA had to prove they could navigate with surgical precision. While Apollo 11 was lucky to find a flat spot to park, the technology tested on Artemis II ensured that when we do return to the surface, we can land exactly where the resources are, within the length of a single football field. SLS versus Saturn V. The Saturn V was the undisputed king of rockets, a 363-foot-tall behemoth designed for a single purpose: brute force. It generated 7.6 million pounds of thrust at liftoff using 5 massive F1 engines that burned a combination of rocket-grade kerosene and liquid oxygen. This was a 3-stage rocket, meaning it was composed of 3 distinct sections that fell away as their fuel was exhausted. The Saturn V was essentially a giant, liquid-fueled skyscraper designed to punch through Earth's atmosphere with enough momentum to hurl the Apollo spacecraft toward the moon. It was a masterpiece of mechanical engineering, but it was also incredibly expensive and difficult to build, leading to its retirement after only 13 launches. Artemis II, however, was powered by the Space Launch System, a rocket that combined historic hardware with modern efficiency. While it stood slightly shorter than the Saturn V at 322 feet, the SLS was significantly more powerful, generating a staggering 8.8 million pounds of thrust, about 15% more power than its predecessor. Unlike the all-liquid Saturn V, the SLS utilized a hybrid design. It featured a central core stage powered by 4 RS-25 engines, the same engines used on the Space Shuttle, flanked by 2 massive solid rocket boosters. These boosters provided about 75% of the total thrust during the first 2 minutes of flight, acting like giant sticks of dynamite that provided the initial kick needed to get the heavy Orion capsule off the pad. The shift represented the move from custom-built brute force to evolvable architecture. The Saturn V was a clean sheet design built from scratch for the moon race, whereas the SLS was built using a shuttle-derived approach, repurposing proven technology like the shuttle's engines and fuel tank design. While the Saturn V could technically carry a heavier total payload into low Earth orbit, the SLS was designed to be more versatile, with the ability to be upgraded for even more powerful future missions to Mars. In 1969, the Saturn V was the maximum limit of what 1960s technology could achieve in a single blast. For Artemis II, the SLS was the beginning of a standardized, reusable engineering framework designed to make deep space travel a sustainable reality, rather than a one-time feat. The death of the toggle switch. The interior of the Apollo 11 command module looked like a chaotic maze of industrial hardware. The astronauts were surrounded by over 500 physical switches, knobs, and circuit breakers, almost all of which had a single, dedicated function. To navigate, they had to manually flip these toggles in precise sequences, often while consulting massive paper flight manuals tucked into their suits. If a light blinked red, they had to cross-reference a physical chart to find the problem. This was a mechanical era of flight, where the connection between the pilot and the machine was entirely manual and physical. Artemis II, however, replaced that wall of switches with a state-of-the-art glass cockpit. Instead of hundreds of individual toggles, the Orion spacecraft featured just 3 large digital display screens. This transition to a glass cockpit, a term used in modern aviation for an aircraft that uses electronic flight instrument displays, allowed the crew to consolidate thousands of data points into a single, clean interface. Rather than hunting for a specific switch, the astronauts used a sophisticated software system to swipe through menus and monitor the ship's health in real time. The shift represents the move from manual operation to automated management. In the Apollo era, the astronauts acted like mechanics, physically opening and closing valves to keep the ship running. On Artemis II, the ship's computer handled the grunt work of managing the life support and propulsion systems. This gave the crew a high-level overview of the mission, allowing them to focus on complex decision-making rather than mechanical maintenance. While the Apollo pilots were limited by what they could see on a tiny analog dial, the Artemis II crew had a digital, 360-degree understanding of their ship, making the glass cockpit not just a visual upgrade, but a fundamental leap in how humans control a spacecraft in deep space. Destination versus distance. In 1969, Apollo 11 was a precision strike. The mission was designed to travel roughly 238,000 miles to reach the Moon, enter a low lunar orbit, and land. While they covered an immense distance, they remained physically close to the Moon's surface, orbiting at an altitude of about 60 miles. The goal was the destination itself, so every mile traveled was calculated to get the lunar module onto the dust as efficiently as possible. Once the landing was done, the mission was effectively a straight shot back home. Artemis II, however, pushed the boundaries of human travel further than any mission in history. Because it was a flyby and not a landing, it utilized a hybrid free return trajectory. This flight path took the crew 4,600 miles beyond the far side of the Moon. By swinging out into this deep space loop, the Artemis II crew traveled thousands of miles further from Earth than the Apollo astronauts ever did. They reached a point in space where no human had ever ventured, turning the Moon into a gravitational pivot point rather than just a parking spot. Apollo 11 traveled the distance required to win a race. Artemis II traveled the distance required to stress test the Orion spacecraft in the harshest environment possible. By pushing thousands of miles past the Moon into the deep space environment, NASA was able to monitor how the ship's communication, navigation, and life support systems handled the extreme isolation and radiation of the void. In 1969, the distance was a hurdle to overcome. For Artemis II, the extra distance was a deliberate laboratory, proving we can survive far beyond the safety of a low lunar orbit. High-stakes braking versus safety slingshot. Apollo 11 relied on a high-stakes maneuver called lunar orbit insertion. As the spacecraft approached the Moon, it had to fire its main engine to slow down enough for the Moon's gravity to catch it. If that engine had failed to fire, the astronauts would have sailed past the Moon into a permanent terminal orbit around the Sun. If it had fired for too long, they could have crashed directly into the lunar surface. It was a must-win moment where the crew had to actively fight physics to stay at their destination. Because the goal was to land, they needed to slow down enough to be captured into lunar orbit and enter a stable lunar orbit to drop the landing craft. Artemis II, however, utilized a much more conservative strategy known as a free return trajectory. Unlike Apollo, which performed an engine burn to enter lunar orbit, Artemis II was launched on a path that used the Moon's gravity as a natural U-turn. As the Orion capsule soared past the far side of the Moon, it didn't fire its engines to stay. Instead, it allowed the Moon's massive gravitational tug to whip the spacecraft around and slingshot it back toward Earth. This difference in orbital mechanics highlights the shift from exploration to safety testing. By choosing a free return path, NASA ensured that even if Orion's primary propulsion system had suffered a total failure, the laws of physics would have naturally brought the crew home without them having to flip a single switch. In 1969, the mission required the crew to perform a dangerous braking maneuver to ensure they stayed. For Artemis II, the trajectory was designed so that the spacecraft was always falling back toward Earth, prioritizing the survival of the crew while they tested the ship's long-range endurance. Mission objective. In 1969, the objective of Apollo 11 was a singular, high-stakes gamble: put boots on the ground and bring them back alive. It was a mission defined entirely by the landing, a vertical sprint to a finish line, to prove that human arrival on another world was possible. Success was binary. Either the lunar module touched the dust or the mission failed, because the primary goal was simply to prove the United States could reach the moon before the Soviet Union. A period of intense rivalry known as the space race. Apollo 11 was designed for what historians call flags and footprints. This means the mission was intended for a short-duration stay, where astronauts would plant a flag, take some photos, and collect samples before quickly departing. It wasn't about staying, it was about showing the world it could be done. Artemis II, however, played a completely different game. This mission was a lunar flyby, not a landing. While Neil Armstrong and Buzz Aldrin spent 21 hours on the surface, the Artemis II crew never actually left their capsule. Instead, they performed a free return trajectory, a specialized flight path that used the moon's own gravity like a tether to whip the spacecraft around the far side and slingshot it back toward Earth without needing a massive engine burn. The shift in objective represented the difference between a sprint and infrastructure. While Apollo was a one-off demonstration of power, Artemis II was a shakedown cruise, a military and engineering term for a trial trip to test a new vessel's systems under real-world conditions. It was a 10-day stress test designed to verify that the Orion spacecraft could sustain human life in the harsh environment of deep space for extended periods. NASA didn't aim for the surface during this phase because they were validating the foundational hardware required for a permanent presence, such as recycled life support, long-range communication arrays, and the heat shield's ability to survive a 25,000 miles per hour re-entry. In 1969, the mission was about the destination. For Artemis II, the mission was about the vessel, ensuring the hardware was robust enough to eventually turn the moon into a permanent base.